Hi, Rafael, Hugo, Karen, and I will present our final project, Prediction of COVID-19 cases in the US using deep learning models. The presentation has the following parts: background and introduction, overview, results of our baseline time series models, RNN models, LSTM models, and finally the conclusions. Our motivation for the project is the threat posed by emerging infectious diseases. Existing early response systems are not refined enough to allow governments to respond in timely fashion to outbreaks. Over the last decade, innovative approaches have been increasingly used to predict outbreaks, including using internet and search engines data. But further research is still needed to refine the predictions. Therefore, our research question is, could the outbreaks of COVID-19 be accurately predicted by deep learning models using digital streaming data? We received 50 files with COVID-19 related data, 1 file per state. In those files, the data had also negative values because Google Trends report searches, COVID-19 searches as set scores, which could be negative. We replaced NAs by a linear interpolation of values using data from both directions. We decided to build models per state as Google Trend data is not comparable among different regions. We have 3 deliverables: our core notebook presenting the individual modeling results of 2 states, New York and California, an auxiliary notebook with a drop-down menu or widget in which you can choose any state and get the results for that state, and an auxiliary notebook with all the graphs and trends of the exploratory data analysis.
Our first time series analysis was simple moving averages. These averages have no predictive ability, but served as an introduction for time series analysis and to get our model baseline. First, we tried simple moving average with 3 and 20 window sizes. You can see on the right how 3 follows the data closely, whereas in 20 window size, there's a little lag. Then we tried cumulative moving average, which considers all prior observation, which wasn't a good fit, as you can see on the bottom right. Then we tried exponential moving average, which gives more weight to the recent values, and as a result of which we expect a better fit. And we compare all 3 models using mean absolute error and mean square error. The best model was SMA with size 3, then SMA with size 20, then exponential, then CMA. But as I stated before, there's no predictive ability on these models. Our first real predictive model is ARMA, autoregressive moving average. This model was not taught in class, but we found it appropriate given the data and the type of time series predictive analysis we were tackling. We had to determine first if the data was stationary or not through ADF statistics and p-values. It was not, therefore we had to apply a differential to convert to stationary and find the correlation terms for the lags, which you can see on the right-hand side. And we use 1, 3, and 7 for the lags, and we realized that 7 offered the smaller RMSE of the 3. This was our baseline model that we use for comparison with the rest of the models moving forward.
One layer RNN model had better results compared to simple moving average models. The fit wasn't perfect as there was a lot of variation in the loss. But we see that the predicted values are following the trend of the test data much better. This may be due to the optimizer used and the learning rate. Next, we can look at the multi-layer RNN model results. Multi-layer RNN results were similar to single-layer RNN results. We understand that both models perform better than the basic models. However, more work needs to be done to improve the quality of the models. With that being said, let's move on to see how LSTM models performed.
Our next experiment was using LSTM models. We started with a single layer model, formatting our data as time series. The result looks promising, but quite not there yet. To improve the results, we added more layers to the LSTM model. Now the graph looks a little better, but still not good enough. Next, we tried transforming our train and test sets to time-step batches using a sliding window with a lookback of 2 weeks and a prediction horizon of 1 day in the future. Now the results look a lot better. The predicted data follows closely the orange line of the actual data. Here you can see in blue the prediction on trained data and the prediction on never seen before test data in green. Trying to further improve our results, we extended the previous model to 4 layers. The result looks better and closer to the actual data in orange. Again, this graph shows the prediction on trained data in blue and the prediction on never seen data in green. In general, we can conclude that we obtain good prediction results, better with multi-layer LSTM models with time steps than with other approaches, except in the sudden larger spikes shown at the end of the graphs. We also used some metrics like mean square error and mean absolute error to compare and verify the performance of the models. We think that future work can be done on our LSTM model to fine-tune it and improve its prediction performance.